Okay, so when we're looking at intermolecular forces, the difference between inter and intra is the inter means between different molecules or atoms. So this inter is the key here. When you travel internationally, right, when you get on a plane and you go to another country, you are going to go internationally, right? So if you fly somewhere else, this is an intermolecular force. Okay. Or intermolecular bond force, same thing. But they usually like to say forces. Okay, so you have another atom or a molecule, and you have a bond between them. Okay, so if you were to look at an intra, this would be, say, if this was a molecule here with two atoms inside it, the intramolecular force would be there, right? The intramolecular. So inter over a longer distance, international, intra smaller. Okay, now when you're wanting to learn, there's a lot of learning in this section. So when you want to learn about these, they have different strengths. And so I like to start at the beginning with the strongest intermolecular force and then work my way down to the weaker ones. So let's, and when you're thinking about something being a strong force, think of it as being permanent. So let's start with an ion, right? Because we know that an ion, so this is an ion here, could either be a positive ion or it could be a negative ion. Okay, and so the negative, that would be an anion, and the positive would be a cation. And these are always charged. So it's relatively permanent. Okay, so we start with an ion. And then that could bond with another ion, but that's not an intermolecular force. That would be an ionic bond, which would be an intra. So what's the next thing it could bond with? Well, it could bond with another molecule, and that molecule, if it was polar, would be a dipole. So what do we mean by that? If we have a dipole here, an ion-dipole force, this is a polar molecule. So we could draw our molecule like this. Let's sort of make it look like water. Because actually, this is an example of one. So we have a dipole, and what do we mean by dipole? Di meaning two, so two poles. So we could have a positive pole and a negative pole. Okay, and often these are not drawn like this, but they're drawn like, it's like this funny weird thing with a negative here, and it looks like an ampersand, and it looks like that with a positive. And so those are our two poles of the molecule, dipole. And just like a magnet attracts sides, so positive and negative sides. So it's like almost like you can think of it as a bar magnet, right? So a bar magnet with a negative end and a positive end. This is the same thing, but it's a molecule. So just like magnets attract each other, opposites attract, so do these ions. And so what happens is you have the concentration of electrons on this side, and that's what makes it negative. And there's a higher concentration, or a smaller concentration of electrons on this side. So we could think of it as being more positive. So the electrons have all moved to this side of the molecule. Remember, the protons don't move, only the electrons move. So although there would be the same amount of, say, protons in the nucleus of these atoms, we have a higher concentration of electrons. And so we have this ionic, this cation, which is positive, and the negative side, and this would then create a dipole. Let's do the bond in yellow. So this would be an ion-dipole force. And so this is a strong force because this is permanently positive and this is permanently negative. And so this is a strong force. So in terms of our intermolecular forces, this is quite a strong one. And so we can think of it as stronger in comparison with, well, our other intermolecular forces. And let's look at an example. So we could have a water molecule. Okay. And so we know our water molecule is a H2O. So we have our oxygen here and our two H's. And they have an intramolecular bond in here, but that's not concerning. What we are concerned with is that this is a negative, right? The oxygen here is negative, so there's a higher concentration of electrons around this oxygen, and that's because we know that this oxygen, well, perhaps you don't know, but there's two lone pairs on this oxygen. There's two lone pairs of electrons, and so we have this high concentration of electrons on the oxygen, and then the hydrogen is comparatively positive, and so that has our plus here and a plus here. So
how can you tell if it's positive or negative?
Good question. So let's quickly then just look at the oxygen molecule quickly. So we know if we look at our periodic table, we'll notice that our oxygen is in group 8. Okay, so let's think of the oxygen. It's in group 6. And so we know that it's got 6 valence electrons. All right, so we can draw them. Actually, let's draw them in blue since we're drawing negatives in blue the whole time. 1, 2, 3, 4. And we know because of the octet rule, there is space for 8, oct meaning 8, for 8 electrons in the outer orbital. And so it's got these 2 blank spaces. So we'll draw those in pink. And then we know that the hydrogen, which it bonds with, there's 2 of them, right? H2O. And we know that the hydrogen just has 1 electron in its orbital, just in that side, in that inner orbital. And so these guys make a perfect match, right? We know that with bonding is all about if atoms are unhappy, they bond together to become more secure and more stable. And this creates a stability when these join together. And so what we have is now a hydrogen, and an oxygen. And we know that whenever you think of a bond, just think of it as 2 electrons. So even though I might draw it like this, it's actually just 2, actually just 2 electrons. Now, they're obviously, we draw them next to each other, but they're not next to each other. They're actually, we know that electrons have opposite spins. But we can just think of that as then a high concentration of electrons over here. And so they're bonded. And so these two electrons together, that's what creates this bond. So when you get to organic chemistry, think of when you get a triple bond, just think of that as having just loads of electrons over here. And so it's not just an abstract concept, this bonding. It's also like in reality, it's just a high concentration of electrons that are bonded together. So a bond is technically just actually electrons that are joined, that are bonded together. So what do we have now? We have these two pairs, and we have then those, so the two that were from the hydrogens, and then the two there. And then so we have these 4 electrons here. So 1, 2, and those are, we would call lone pairs. Okay. And so they'll often draw it as dots. And so that is why you actually, this hydrogen molecule is drawn as bent, because you have the oxygen and the hydrogen. And now I'm just, for simplicity's sake, going to draw the 2 bonds, and we know these are the 2 electrons. Here, we'll draw the 2 bonds, these intramolecular bonds. And these 4, what they do is the electrons are negative, and what they do is they push these other 2 away. And so we have these 2 here that are like almost, they're sort of pushing these other, because remember, opposites attract and like charges repel. And sorry, yeah. And so these electrons, they actually push away. And so they push these, the lone pairs push the other electrons upwards. And so we have this, hydrogen is always drawn as a bent molecule. So hydrogen is actually bent. Sorry, not water is bent. So that's, and so now when we look at this, we go, oh, okay, look, high concentration of electrons around the oxygen. And so that's how we know that it is negative. Okay. And the hydrogens comparatively now would then be the polar side. Okay, so now we have this water, and we think of this water as not just one molecule, right? There's several, but I'm just, for simplicity's sake, only drawing one. And then what you could do is, so let's say you had a lot of these molecules. I'll draw one, but without one more without all the details. And so you have these water molecules, and let's say you pour in some salt, which is NaCl. So now we're actually looking at it more practically. It's not just abstract. The Na is positive. We know from our, it's on the group 1 of our periodic table. So those are all positive. Chlorine, group 7. And so that is then negative. So it's joining together, and then it goes into the water. So it's now and salt, it's in a stable crystal lattice. You dissolve it. What happens is with the water, and we'll get into this, but the hydrogen bonding of water actually causes the ions to separate. And so we will have these chlorine ones all going around the positive, right? Because the opposites attract. And so you'll have a whole bunch of Cl minus. Let's draw them around here. Cl minus, Cl minus, Cl minus. And so those will all be attracted to the positive because they are negative. And so we'll have this And we draw these intermolecular forces with a dotted line, because they're not as strong as the covalent forces within a molecule. And so there we have it. And then we have the sodium ones. Well, those are all going to go to the negative, aren't they? And so they'll all be around this negative oxygen. And so you'll have the sodium cations all around the, it's becoming a bit of a mess, but hopefully you can see it. So those will be around the negative. Okay, so if we were to draw it a little bit more simply, we could have these, let's just say the molecules like that. Positive, negative, and then the positive ions all move around the negative, and then the negative ions move around the positive pole. Okay, so the nice thing with these forces is they are what they say they are. So an ion dipole is an ion, which is positive or negative, and a dipole molecule, which is a molecule that has a positive and a negative end. So it's dipolar. Okay. Okay, so it's a strong bond because the ion is always positive or negative, and the dipole has this permanent pole. Okay, now let's go to the next one. And let's do a dipole-dipole. Okay, now because I've just done water, let's keep it at water. Okay, so I did the dipole in dipole. And so we have these dipole molecules. And let's make it water again. Let's do that in blue. So dipole, so this is now actually just between polar molecules, because it's dipoles and dipoles. So it's the water is the most common example cited of this, because we know that water is a polar molecule. Sorry, the water molecule is polar, the H2O molecule is polar. And so if you have a bunch of these, we've already explained that they have negative and positive ends, so I'm not going to go into that. I'm just going to draw the positive ends. Okay, and so now whenever we draw these, by the way, we always draw a snapshot, but these are dynamic. They're moving all the time. And so when you have this ions in solution before, that solution is constantly moving, and so you're actually having molecules bonds breaking and forming the whole time. And the weaker the forces, the faster they break and get back together again. So let's look at now these molecules. So what they're going to do is the positives are going to repel each other, and they're actually going to align in order to so that the negative goes to the positive, and so this should have, I don't know why I drew that positive, so it should be negative. Just it's negative. That would be negative. So here we have the negative sides of these dipoles attracting to the positive. And so we could move, let's move this one. And so they would then move around to align themselves to be attracted to, I could go there. Oops. And so there, this positive end here. Okay, and so the molecules align themselves to be in order to be attracted, so that the attraction between the positive and the negative happens. And so we have these positive, negative, negative. And notice that these negatives are pretty close together. And so if we think of it as a dynamic molecule, actually sort of this might sort of move a little bit, and so that would move to there. But when we draw it, of course, we just draw the snapshot. Okay, and so we can just imagine that these are moving the whole time. But the main thing is that our negatives and our positives are attracted to each other. And so we have our bonds here. Okay, so we have polar molecule with a polar molecule. So that's what the dipole means. So when you see dipole, just think of polar molecule. Pole, di, two. Polar molecule, and a bond in between them. And they will be the positive of one and the negative of the other. Okay, so this is a dipole-dipole interaction. And what we will now look at is a special type of dipole-dipole, which is indeed this water, which would happen in this water. And so a special case of dipole-dipole is called hydrogen bonding. Hydrogen bonding. Now, hydrogen bonding occurs between hydrogen, obviously, so we'll say H. So let's draw the hydrogen sides in pink, right? Hydrogen bonding can happen between an H and the NOF gases. So when you look at your periodic table, you'll see nitrogen, oxygen, fluorine. So let's write those down. Nitrogen. Let's do them in white. Nitrogen, oxygen, fluorine, NOF. Okay. Now, when we look at that periodic table, the nitrogen has 5 valence electrons, the oxygen has 6, and the fluorine has 7. Right? So let's try to do the valence electrons here. It would be 6 valence electrons, 7, not 6, 5. 5 valence electrons, 6 valence electrons, and 7 valence electrons. Now, more electrons, more attraction, right? So this fluorine, the fluorine and the hydrogen, if we were to draw this bond and we make the thickness represent the strength of the bond, it's going to be very strong. So the HF bond, in terms of your hydrogen bonds, is the strongest one. Then you would have your oxygen, should be the second strongest, because it's only got 6 valence electrons. And then your nitrogen is going to be a bit weaker because it's only got the 5 valence electrons. So if you get asked in a multiple choice, which are the strongest between hydrogen and fluorine, hydrogen and nitrogen, hydrogen, oxygen, you know that it'll be fluorine. And all you do is just look at your periodic table and go, fluorine, I know, has lots of electrons. It's going to be attracted a lot to this hydrogen. Okay, so getting back to the special hydrogen bond, we actually see it over here. This here is your hydrogen bond, because you have your hydrogen here. So let's draw the H there. And your oxygen part of the water molecule over here. Okay, and so the H and the O, H's and O's, bond together much more strongly than a normal dipole-dipole bond. So a hydrogen bond is a dipole-dipole bond, but it is an especially strong one because of the number of valence electrons, so it can make multiple bonds. And that means that water has special properties. So if we think of water as when you put the ion, when you dissolve the water, NaCl, the table salt, sodium chloride, into the water, the strength of these hydrogen bonds within the water molecules are strong enough to sort of push the ions apart, and you have this dissolving process. And so this makes water, means that you can dissolve things in water quite easily, as long as those things are polar. And that we don't need to go into it, but just remember the main thing when you're thinking of things dissolving is like dissolves like. So we have a polar molecule here, water, dissolving a polar substance, NaCl, which is polar because it's got Na plus on one side and chlorine minus on the other. And so like dissolves like. So that's the one property. So the other property that you need to know about that's created by these hydrogen bonds is the boiling point. So if we think of this hydrogen bonding being stronger, then we know that we need more energy to break these bonds. And so heat is a form of energy. And so more energy, more heat required to break these bonds. So if you get a question like, why does H2O have sorry about the noise.
No worries.
Why does H2O have a stronger boiling point than, say, H2S? Well, it's because of these hydrogen bonds. And so this one has a 100°C boiling point, and I don't know what H2S is, but I know that it is less than 100°C. Okay, so that's the dipole-dipole bond. And we can see that because the poles are permanently polar, so permanently plus and permanently minus, it's a strong bond. Now let's look at, we saw an ion-dipole bond. Let's look at an ion-induced dipole. Now, as I said, these things do what they say. When I say ion-induced dipole, it means that something was induced, something was created. It wasn't just there. There wasn't a dipole before, but suddenly we got one. And the ion is the thing that makes this this molecule that is non-polar. So let's think of the non-polar molecule. We'll do it. I think I listed in yellow. Non-polar, right? But it becomes a dipole. So how does that happen? So we have this non-polar molecule. So let's think of oxygen. Okay. So oxygen is double bonded. Double bonded molecule. And there's an evenness of electrons. Because if you think about it, oxygen and oxygen, there's nothing to choose between the two. So we know that it's non-polar. It also has the same electronegativity. And we know that the difference in electronegativity determines if it's polar or non-polar. And the fact is, if oxygen has the same electronegativity as another oxygen, the difference between them is 0. And so it's non-polar. Okay, because there's no difference in electronegativity. And that tells us it's non-polar. So if you were to draw this molecule, we could draw it, and we could draw it with a bunch of electrons. Now, for simplicity's sake, I'm going to go and draw it like a sort of the plum pudding model of it, which is completely wrong, right? Where electrons are all kind of spread out evenly. We know that's not the case, but we know that they're sort of spinning. But just for simplicity's sake, let's just say that the electrons are evenly distributed like this. We do know that they are evenly distributed in terms of there's no poles between these two sides. But we know that actually there's quite a lot of electrons around the center. That doesn't make it a pole. So we have an oxygen molecule. And let's say that we have something like iron, right? Fe3+. We have an iron, right? It's a cation. And this approaches. Here. Okay, so what is going to happen is, because this ion is positive, these electrons are all going to be attracted. They're going to say, oh, we like to be near this guy. So sorry, I don't know why that's not moving. But you get the point. They all go there. And so this side of the molecule becomes negative. And so we have this induced dipole, and we'll just, rather than move, let's get back this time. Nope, they're not going to do it. Okay, so we have the concentration of electrons on one side of the molecule. And so this side then becomes positive. Okay, and so we could have another type. So if this was sodium chloride, it's a bad example, but we would have then this side being positive, and you could have other ions that are negative being attracted to this side. So let's just draw negative ions for now. So you would then have negative ions here. Negative ion, and so you have this now temporary bond here and here. Now, what could happen is you could then, because this is a dynamic solution, you could have an ion coming over here. And what that would do is, because it might be a bit closer and moving in, they would then get attracted to this side. And so these because this isn't permanent, these are not permanent poles. They're kind of being induced and broken. And this is not as strong as your ion-dipole force, where you've got a permanent pole. These are induced dipoles because the molecule is actually normally just polar. But you make it, sorry, non-polar, but you make it polar because of this interaction with the ions and the electrons moving. And so you have this dynamic system of these bonds created the whole time. The main thing is that this is an ion-induced dipole force, and we know that means it's between an ion and a non-polar molecule. So the induction takes place in a non-polar molecule, because if it was a polar molecule, it wouldn't need to be induced. It's just got that positive and negative end. So we can, in order to remember this, we can actually think about how this might work in something in reality. So if we were to think of our blood, and we know that the blood is, in the blood, we have oxygen, right? We know from our biology lessons that when your blood goes first to the lungs, it gets oxygenated in the lungs, and it goes back to the heart, and then the heart pumps it out the aorta with its nice thick walls, and that goes into the body, and then it gets used up in the body. We use all the oxygen, and then it goes back, and it's a different color. It's now oxygen depleted, and it needs to then go back to the lungs. And this is happening every half second, or it's happening the whole time, just to keep us surviving. This incredible process is happening. But importantly, this oxygen needs to be transported, and so we need an ion, and this is why we talk about ion deficiency, not the ion ION, but the ion Fe, right? Ion, or we say Fe ion. And so what happens is you could have this Fe3 plus, which let's just draw it as a plus. And so that then helps to transport the blood by then bonding with our, and then we have, I forget the type of blood, which is the blood cell that carries the blood. Doesn't matter. Red
blood cells, I think.
Yeah, the red blood cells. So, and the ion is important in this transport because it creates an ion, it creates a bond, which we just illustrated there. And we have this bonding of these ion in the blood. Okay, but it's helping us to transport the oxygen around the body, okay, and other things as well. So yeah, it's quite a complicated, this biochemistry that happens. But we know that we study chemistry so that we can understand these interactions. Okay, so we have the ion creating a dipole, inducing a dipole in the oxygen molecules, and then being able to bond. So this is not quite as strong. So we're going from stronger to less and less strong. Now, let's go to our dipole-induced dipole. Okay. What color did the dipole say? Okay, so here A dipole, we have a polar molecule because that's a dipole. But now this induced dipole was not polar, it was non-polar. And in the same way that, so this is a non-polar molecule, so we can draw that in the light green that we had before, non-polar. And so we have this bond between these, a polar molecule and a non-polar. And it works in much the same way. So I'm not going to spend, but let's think of it rather than do an example and then, sorry, rather than do the generic and then do an example, let's just do the example and we'll use water. Because we now know that water is a polar molecule with a positive end, which I think we were doing in, yeah, so positive and positive here. And we have a negative end here to the oxygen. Okay, now let's again use the oxygen molecule with our electrons. Okay, so these electrons are going to be attracted to the positive side. And so we will have a movement of these electrons. And so the electrons on the one side will kind of disappear and will not disappear. They'll move over to the side that's close to the hydrogen. So they'll be kind of there. They'll be concentrated on one side. And so we'll get this ion-induced, this polar dipole-induced dipole. So this positive side induces a polarity there. And so this otherwise non-polar molecule becomes polar. And we have this, and this is very, very practical, especially because we can now think of the dynamic situation of, let's say that a water molecule comes here, sorry, and so the electrons then jump to the other side. And so you have maybe a bond now joining here and the electrons all coming over here. And then this one breaking. And so this kind of disappears. And this then becomes a positive. And so it moves away. And so things constantly moving. We have a positive now here. But when you see it, you're always going to just see a snapshot. They're just going to show you a snapshot of this situation. And remember, you'll always have the negative end being attracted to the positive and creating this dipole-induced dipole force. Okay, now what's interesting about this water situation is when we think about global warming. So let's see, let's draw, this is the water here, right? And we have all these water molecules. And we know that fish, just like us, need oxygen to survive, right? These are all the water molecules. And then we have the oxygen inside the water. And the way that it's being held inside the water is these dipole-induced dipole forces. So we have all these forces that are just not too strong, but they're strong enough to keep the water, the oxygen suspended in the water. Now, what happens when we heat the water?
Evaporates.
it evaporates, right? Okay. Or if we just heat the water, but it doesn't fully evaporate. Well, so what happens is you boil the kettle and we have some water evaporating, but you're still drinking, there's still water to drink, right? So some of it's evaporated. But what happens as well is that because these are not incredibly strong forces, we also have the oxygen leaving the water as well. So you also have not the oxygen that's attached to the hydrogen molecules, but rather the oxygen molecules themselves, the O2. Let's actually say that's O2. I should have been writing that the whole time. When you think of these, just think of it as O2, right? It's 2 oxygen molecules. And so we have this O2 leaving the water. And so the concentration of our oxygen inside the water goes down. So if you keep boiling the kettle, the reason I know this, I thought about this is because my wife works for a tea company. And the tea master from Five Roses, the guy who signs all the tea boxes, he always says you shouldn't boil your water too often when you make tea. You should, first of all, it saves energy, but second of all, it's better for the flavor. So when you boil your kettle, you should pour enough for however much tea you're having. So if it's two or three teas, you put 1 liter and you boil it. Because when you boil it for a second time, the oxygen is further depleted, and so you can have less oxygenated water, and for some reason that changes the flavor of the tea. But it's not going to kill us. But what is going to kill us and the fish is the global warming. Because what happens is when the water gets heated, the oxygen leaves the water. And so a change in temperature upwards does much more harm than cooling. Because we know that actually colder water is more oxygen rich. So like if water is like 3 or 4 degrees Celsius, and it's actually got a lot of oxygen. And so the fish can survive if the water cools. But they really struggle as the temperature of the seas increase. And so we got to think about that. Well, it's just something to kind of help. If it doesn't cause you to be an activist, at least it'll help you kind of remember what are dipole-induced dipole forces. The next one, so we've done an ion inducing a dipole in a nonpolar molecule. Then we've done a dipole inducing dipole. Now let's think of and they call this a different name, but I'm going to give you the long name first. It's called an induced dipole induced dipole induced dipole bond force. Okay, and so they scrap this and they go, let's just call it van der Waals. Much easier. It would be better if he had a shorter name, but his name at least is shorter than this thing here. Van der Waals forces. Okay, and these forces are actually London forces is what we're going to look at. Actually, sorry, London force. It actually is shorter. London forces. That's better.
Are they the same thing, London and van der Waals?
So all of these forces are van der Waals. These are actually London forces.
Okay.
Sorry. The induced forces are van der Waals. The London forces are these. Not discovered in London. There was a guy named London. So actually much better. His name is much shorter. And it's easy to remember because it's the same as a city. So these London forces, so this guy figured out, right? So we have oxygen. And let's just say that we have pure oxygen and we were to look at it as a gas, right? So this is a whole bunch of oxygen molecules. Why does it stay together? Like, why doesn't it just non-polar? Why doesn't it just kind of disperse? We notice that gas kind of stays together a bit. And so what this guy figured out is that because electrons are constantly moving. So I drew a very simplistic thing where I drew the electrons all like a kind of uniformly. But we know that if I took a snapshot, if I took a photo of this molecule, I'm not going to see that. Because these electrons are randomly moving around, if I was to take a photo at one point, I might notice that there is a slight polarity to this molecule, where the electrons at some point are a little bit on the one side. So you have this, it induces its own dipole in a way, but it's very weak, right? So that's why they call them weak forces. Weak forces. And so we have this temporary, so it is two non-polar molecules, so we'll just write non-polar, non-polar. Just get it more and more wound up. Non-polar. Okay, so this then, now you have a slight polarity in this one molecule, which then, because you have a bunch of molecules together, this negative would then attract, would then repel the electrons in over here, and so you would then have a polar, an induced dipole over here. Okay, but these are super weak. So they're breaking all the time and forming again, because now you have another molecule over here. And suddenly this might have a slightly stronger dipole, which is negative over here. And so I'm not going to draw it again, but you can see that these it's constantly changing. And so they're very weak because they're very temporary. Right, so it's temporary. So we can think of them as temporary. And again, we can think of the practical example of oxygen gas, which is somehow staying together. And that is because the electrons in the oxygen atoms are moving and therefore being sort of somewhat polar and at certain times, creating then a weak dipole, non-polar, induced dipole force, or London force. I don't know, does that make sense?
Yeah, it does.
Okay. So we see the strength of these molecules, the strength of these forces is based on the permanence. So just to go back from the beginning, so we had these permanent ions and dipoles, and then we got to non-polar molecules at the very end, which do not have polarity, but they do sometimes, and London figured that out. Okay, so that is intermolecular forces or intermolecular bonding.